Hi. In this problem, we're going to get some more practice working with Markov chains using this particular Markov chain. So we have 4 states in this chain, 1, 2, 3, 4. And if you look at it, the transitions sort of go in a clockwise manner. So 1 goes to 2, 2 can sometimes stay within 2, but eventually it will go to 3. 3 will go to 4, 4 can stay at 4 for some time, but then it will go to 1, and then it will keep cycling through. And we're given these transition probabilities. And if we wanted to, we could use these transition probabilities to calculate the steady state probabilities for each state. But the problem kind of saves us that effort and already gives us what the steady state probabilities are. Okay, so the first part of the problem asks us to find the expectation and variance of a random variable k, which is defined to be the number of transitions starting from 1 until you get back to 1. So right now we are currently at 1 before the first transition, and we want to know how many times on average it will take us to get, how many transitions on average it will take us to get back to state 1. And if you think about it, that sounds like the mean recurrence time that we talked about in class. And in fact, we could actually use that recursive formula to calculate what the mean recurrence time would be. And that would give us the expectation of k. But that formula doesn't give us what the variance of k is. And in this particular chain, because of its structure, this cyclic structure, we can actually directly compute what the random variable k is. So it just takes a little bit of analysis. So the first thing that we can do is we can actually think about what transitions are necessary in order to get us from 1 back to 1. Well, we're starting at 1, and we know for sure that the next transition will take us to state 2. So that will cost us 1 transition. Starting from state 2, we can stay in state 2 for some number of times, but eventually we'll leave and go to state 3. Well, we don't know exactly how many transitions that will be, so let's assign it a random variable k2. Now, after k2 transitions, we'll be at state 3. From state 3, we know for sure that after exactly 1 transition, we'll go immediately to state 4. So that's 1 more transition. And then starting from state 4, there's some random number of transitions and before we go back to state 1. And let's call that k4. And now, if we think about it, k2, we actually know what the distribution of k2 is, because k2 is actually just geometric, with the probabilities of success being equal to 2/3. So why is that? Well, once we get to state 2, we want to know k2 is just the number of transitions until we first go to state 3. Well, that really is just exactly what a geometric is. The probability of success, the success in this case would be going to state 3. That probability is 2/3. And so that's why we get it's a geometric with a probability 2/3. Similarly, k4 is also geometric. And it has a different probability of success. Its probability of success is 3/5 because that's the probability that you'll go from transition from state 4 to state 1. All right. So now that we know that, let's actually figure out what the values that we're interested in are. And now expectation of k, we can use linearity. 1 plus 1 is 2. And then we need the expectation of k2 plus expectation of k4. Well, we know from earlier in the course that the expected value of a geometric is just 1 over the probability of success. And so 1 over the probability of success is 1 over 2/3 is 3/2 for k2. And 1 over 5/3 is, 1 over 3/5 is 5/3. And so the total number of transitions on average it'll take to do 1 loop across is 31 over 6, which is about a little over 5 transitions. Okay. Now, the other part is to calculate what the variance is. Now, this is something that the mean recurrence time formula that we learned in class would not allow us to calculate. But because we actually know exactly what comprises K, we can actually calculate what this is. So the constant's 1 plus 1, that doesn't impact the variance. K2, so what we just have is the variance of K2 plus K4. Now, if we think about it, K2 and K4 are independent because the number of transitions it takes you to go from state 2 to state 3, that does not have any impact on the number of transitions that it takes to get from state 4 to state 1, right? Because this is a different part of the chain. You've left here, you've gone here, and now you're here. Because of the Markov property, right? The past history doesn't really matter. And because of that, K2 and K4 are in fact independent. And so the variance of a sum of independent random variables is the sum of the individual variances. So we can simplify this and say this is just the variance of K2 plus the variance of K4. Now, what is the variance of K2? Variance of K2 is the variance of a geometric with p equals to 2/3. And remember, the variance of a geometric is 1 minus p over p squared. So in this case, it's 1 minus 2/3 over 2/3 squared. And similarly, for K4, it's 1 minus 3/5 over 3/5 squared. And now if you just simplify and do some arithmetic, you get that the final answer is 67 over 36. Okay, so this was an example of one particular case or one specific Markov chain where you could actually do some clever analysis and figure out that you can actually define exactly what the recurrence time is. And because of that, you don't actually need to use the formula. You can directly calculate what this is. And in addition, you can actually calculate what the variance is. Okay, now let's go on to the second part of this problem. The second part of the problem is related to the 999th transition, the 1000th transition, and the 1001st transition. And so what it's asking you is, what is the probability that the 1000th transition is different from the 999th transition, and also the 1000th transition is different from the 1001st transition? So let's, instead of saying that over and over again, let's define some random variables. Let's call xn the state that you're in after transition n. Okay, and now let's define the event of interest. This is what we're trying to find. The event of interest is that x1000, so the state after the 1000th transition, is not the same as x999, and 1000 is not equal to x1001. What we want to find is the probability of this event. Okay. Now, how do we do this? Well, the reason we're talking about such large transition numbers is that we want to be able to use the steady state transition probabilities, or the steady state probabilities. Because we've already done 1,000 transitions, let's just we can now relatively reasonably approximate the probability that you're at any one of these states by the steady state probabilities. So we've kind of forgotten about which state we started out at. The Markov chain has mixed sufficiently. So let's now just use the law of total probability and break it up into different cases. So the probability of this event actually occurring, we can think of it as the combination of different possibilities. So let's think of it as, I guess this is actually, to be technically, this is actually just approximately equal to. So it's the probability that you have that event A occurs, conditioned on that the 999th state, the state after the 999th transition is state I, times the steady state probability that you're actually in state I, which is basically gives you what the probability of this conditioning is. Because you've already had 999 transitions, you can approximate using just the steady state probability. And you do this for all 4 different possible states that you can be in, and that covers all the different cases. All right, so now let's think about what these 4 different scenarios give you. So let's think about state 1. So suppose I is 1. If you're in state 1 after the 999th transition, well, you're guaranteed that the 1000th transition will take you to state 2. So x 1000 is for sure going to be different from x 999. So that's probability 1. And now you also want x 1000 to be different from x 1001. Well, x 1001 can be either state 2 again, if you do a self-transition, or it can be state 3 if you transition away. Now, you want it to be different, so you want it to transition away to state 3. That happens with probability 2/3. And then the last thing is, what is the actual probability that you're in state 1 after 999 transitions? We approximate that using pi 1. Pi 1 is 6/31. So that is the first part of this. Now let's consider you're in state 2. Well, if you're in state 2, you want the next transition to take you somewhere else. So for that to happen, you need to go to state 3, which happens with probability 2/3. Once you're in state 3, then for sure you're going to go to state 4 because that's probability 1. And then the last thing is, what is the probability that you're in state 2? It's approximately pi 2, which is 9/31. Now we'll continue. Let's think about state 3. For state 3, you know for sure that you're going to go to a different state, state 4. And then after that, you want to be at a different state still, which means that you need to transition state 1. That gives you a 3/5 probability. And then multiply that by pi 3 is 6/31. Then the last one, if you're in state 4, you need to go to state 1. And then once you're in state 1, you know that you're going to go to state 2. So that's going to be different. You get 3/5 times 1 times pi 4, which is 10/31. All right. Now you do some more math, and you get that the final answer is 98/155, which is approximately 0.6323. Okay. And that's the final answer. And so because we're dealing with large transitions, large transition number, we can simplify our lives and use the steady state probabilities as a good approximation. And the last part of the puzzle in solving this is to actually think about what needs to happen in order for this event A to occur. And that is actually relatively simple with this particular Markov chain because of the cyclical structure. And so by analyzing that, we can calculate what all these probabilities are.